For the next few questions, we're going to look at the mixture of redox or a redox mixture, not a single couple, but two different couples where they're mixed. And so we have an overall reaction between them. And we're going to look at the calculation of the equilibrium constant and what else we can get from the equilibrium constant if it was information not given. Now, we already saw in our previous recording how we can get the corrected potential if the concentrations of either the oxidant or the reductant in any half reaction was not 1 molar. And we used the Nernst equation. Now, this is for a single reaction. Okay, this is not for the overall reaction, but you could do the same thing for the overall reaction, except that the number of electron transferred would be the overall electron transferred. This is the corrected potential. You get a minus sign here, and then products divided by reactants. If you put a plus sign, it'll be reactants divided by products, and always write the reaction in the form of a reduction equation. And if you have already an overall reaction where you don't have number of electrons, you have to figure out what the number of electrons are. Once you have an E for the corrected potential for each of the two different couples, then you would choose the higher E that will undergo reduction, the lower E will undergo oxidation, and you get an overall global balanced equation. From that, you get also the delta E, or the change in the corrected reduction potentials, which is the E reduction minus E oxidation. And of course, we already chose it to be positive because we chose the higher E to be the reduction reaction. Nonetheless, if they already give you an equation, this might not be the case if they have already given you the equation. You can be asked to get the delta G or the K for the reaction, which is the equilibrium constant. If you're asked for delta G or K, actually delta G, the K, you only use delta E naught, even if the reactions are not in standard state. But for delta G, you could get delta G naught for standard conditions and delta G at non-standard conditions. Again, whether you see delta E or E of the cell sometimes, or E of the reaction, we look at it the same way. This delta G is the free energy, and you can have it delta G naught or delta G alone, where you use the delta E, not delta E naught. However, watch out, K is only delta E naught, only delta E naught. Okay, balance the following and tell me the equilibrium constant. You have an equation. Split that equation into two halves. Of course, put the AGs together and put the chromate with the AG, put the tin together, and see where reduction is occurring and where oxidation. Or you can go ahead and find the oxidation numbers and decide if you have reduction, where you have a gain of electrons from +1 to 0 for AG, or a loss of electrons, for example, for the tin. I personally like to split the reactions up and then balance it and see where the electrons are going. But you could do it either way. Here, they didn't give me any concentrations, and therefore I can just get delta E naught, which is delta E naught reduction minus delta E naught oxidation. Whichever half reaction undergoes reduction, it's the AG, and the tin is undergoing oxidation, as in the number of electrons that are being gained or lost. Notice I didn't multiply the E nodes by any number. I didn't multiply it by 2, nothing. As is, you don't do anything to the E node, even if you have to multiply the overall equation by some constant. Get the K from log K equals N delta E naught divided by 0.592. Now, here you have to look at the total number of electrons transferred N, or you would say that the number of electrons will be 1 times 2, which is the number of electrons transferred in the first equation and the number of electrons transferred in the second half reaction. I like to look at it in the form of an overall, how many electrons are transferred, times the delta E naught, which you just found, and get the K. Notice the K is a large number. I can't right away say that K is complete based on the fact that it's greater than 10 to the 6. But nonetheless, this is by assumption, it is complete because the K is a large number, okay? And make sure that the K is always calculated from the delta E naught. Of course, this reaction is spontaneous because the delta E naught is greater than 0, and that's because we are assuming we're in standard conditions. This is the same thing. You just have to try it. You have the answers. First of all, it's not a balanced equation, so you have to try to balance it with whichever form that you like. See who's undergoing oxidation, who's undergoing reduction, and get the total number of electrons exchanged, which in this case, one will have 8 electrons gained, the other has 8 electrons lost. Overall electrons exchanged in this reaction will be 8. And if I need, so I have a balanced equation now, get the delta E naught. Regardless, again, I use the delta E's of each couple, irrespective that one couple I had to multiply by 4 to get a balanced equation. I didn't multiply by 4 for the E naughts. Get the K from the same equation, log K equals N delta E naught divided by 0.592. The N, again, is the total number of electrons transferred, and we are done. Okay, this is a huge number, 10 to the 220, so definitely more than complete reaction. Now you have a little bit of harder questions, and I need you to pay attention to these very well. Here, let's look at this. We have a solution which gives us a volume of 10 milliliters of tin 2 plus at a concentration 0.1. So automatically, I'm not in standard conditions. And a volume V2 of 10 milliliters of Fe3 plus, and again, a concentration which is not standard. Elucidate the constituents or the species present. When you hear constituents, that's the species present of the solution, and calculate the concentration. Sometimes they say the composition of all species. They don't tell you concentration, they use the word composition. Calculate the potential at equilibrium of the redox couple in the solution. So they gave you the E naughts for both half reactions. Notice that there is, they didn't tell you how they're mixed, if they're in, this has to be a one pot. So if they're mixed together, that means they are in one pot. But irrespective of if the redox couple are in one pot or not, the calculations are exactly the same. We don't really switch in a different form of the calculation. It's exactly the same. First, I need a balanced equation, okay? And we are in non-standard conditions, yet E nodes, I put here the Fe couple and the tin couple in their E naught form. Am I right away allowed to do that? The idea is no, I am not, okay? Because you have to correct for the E nodes. So you can't right away just decide, It will undergo reduction here, and the tin will undergo oxidation because it has a lower E0 value, and Fe has a higher E0 value. I can't say that immediately. I can't say that, but the only thing I have in the reaction mixture is Fe3 plus and tin2 plus. So I can't react something that I don't have. I only mixed Fe3 plus and tin2 plus. So that's pretty much why I can write an equation without doing the E calculation for this. So with this equation, we put the Fe3 plus, this is going to be my reduction, and the tin2 plus, which is going to be my oxidation, because those are the reactants that I have in solution. Okay? I'm getting a global reaction, and that's my global reaction. I had to multiply the Fe by 2 in order to balance the equation. Of course, we know that log K is the number of electron transferred, delta E naught divided by the 0.0592, and get the log K. The number of electron transferred is 2 for now, both of them. And again, you could say 2 times 1, which is still 2, but again, multiplied by delta E naught, which is E reduction minus E naught oxidation, which is 0.77 divided by 0.15. Notice, even if I'm under non-standard conditions, I do not have to correct this. This is always delta E naught. Find the K, and you get a complete reaction, okay? Because the K is fairly large. Now they want the concentrations or the composition of the solutions at equilibrium, okay? We have the equilibrium constant K. I also can get the initial concentrations of the mixture once mixed. Both the tin2 plus and the Fe3 plus have the same concentration, which was 0.1. We use the same volume initially, and we mix them in the same solution, which is 10 plus 10, which is 20 mils. So the number of moles will be 0.1 times 10 milliliters divided by total volume 20 mils, and you get the initial concentration of both the iron and the tin. Of course, you know that when the reaction proceeds, this is going to do minus 2x, minus x, plus x, plus x. But because the reaction is complete, okay, you could easily solve for x, and so this is minus 2x, solve for the x. You will notice that the iron is our limiting because it's 0.05 divided by 2. That's the equivalency moles. So that's going to tend to 0. This is going to be 0.25. Of course, go ahead, solve for x first. You can say minus 2x equals 0.5, solve for x, and then substitute. This is going to be 0.025 and 0.25. Now, if I really want the iron concentration, at this moment it's 0, but there's no such thing as 0. We call it epsilon, and sometimes we call it 2 epsilon, which is like the back reaction. But in any complete reaction in the forward direction, the back direction is very minimal for if you already have a certain concentration present. Nonetheless, regardless of what you want to call it, epsilon or 2 epsilon, it's 0 at the moment, which is some number concentration of Fe3 plus. If I want to find this Fe3 plus, I go back to my K. At equilibrium, we have the tin, we have the iron 2 plus, we have the tin 4 plus, and this K is from the total global reaction expressions, products divided by reactants to the stoichiometric coefficient, each of them, and then solve for the Fe3 plus by substituting each of these concentrations. get an answer, your Fe3 plus will be the following: 1.68 times 10 to the minus 12. You try it, and I'm just going to put 2 epsilon here because that would be official, but again, we don't use the word epsilon anywhere in these equations. If we were to study complex reactions, we really would have used it a lot. Okay, this next section is by far very, very important, which is to look at what is the equilibrium potential, or the potential at equilibrium. Well, we all know that there is no longer any reaction, net reaction, if you will, between the iron and the tin once we've reached equilibrium. The forward reaction is like the backward reaction, and we have no change, net change in concentration of the species once we've reached equilibrium. And the delta E is going to be 0. Now, delta E means E red minus Eox equals to 0, and therefore Eox, whichever half reactions undergoing oxidation, should equal the E red, whichever half reactions undergoing reduction, which is, we call it the E of the solution, or the potential at equilibrium for this solution. Now we apply the Nernst to get the reduction potential at each electrode in a redox couple. And regardless if the electrode is undergoing reduction or oxidation, we only get the reduction potentials, okay? So for the tin couple, the reduction potential is the E naught of the tin couple plus 0.592 divided by the number of electron transferred for the tin couple, plus log of the reactants divided by products for the reduction reaction, or ox divided by red. Substitute, notice we substitute the concentrations at equilibrium, and in this case they happen to be the same, and thus the E corrected potential happens to be the same as the standard potential for the tin couple. For the iron couple, we also look at it. The E for the couple of the iron is 0 E naught plus the 0.592 divided by 1, because there's only 1 electron transferred for the reduction half reaction for the iron, plus log of the reactants divided by products for the reduction reaction, which happens to be the ox divided by the red. Plus sign here, not typical of the Nernst, okay? And solve, you get the same answer. Here, of course, the E naught is not the same as the E for the iron, but still, E of the tin couple equals the E of the iron couple. Okay? And so what is the E of the solution? Yes, it's 0.15. Another number, number 10. Okay, we also have here a mixture in a one pot, Ag, iron 3 plus and iron 2 plus. And they put different concentrations of these species at 25 degrees Celsius. And they tell us that when the system reaches equilibrium, the Ag at equilibrium is 0.08. Okay? So they gave us already the concentration at equilibrium for the silver. They ask us to determine the equilibrium constant, then the E naught. Here, notice they're asking me to get the E naught for this couple. This is the first time this was asked. Usually we have the E naughts, which would have saved us a lot of, hassle. But this case, we don't have the E naught and we have to get it. Find the potential at equilibrium, and they gave us the E naught for the iron. So first, they're asking us to determine the equilibrium constant. So if I have to get the equilibrium constant, well, I have the iron, E naught, but I don't know the E naught of Ag. Should it be up on top of the iron or below the iron? We have no idea where the Ag should belong, okay? So I don't know if it's going to undergo reduction or oxidation. But And I also cannot get the E naught right away, so I can't get the equilibrium constant right away. But we are given that at equilibrium, the Ag is 0.08. If it was, notice again, just for a moment, if its concentration was 0.1 initially, and at equilibrium it became 0.8, what does that mean to you? It means the Ag plus decreased. And if it decreased, it means that it's on the reactant side on the most probable end, okay? And since its concentration decreased, it's likely to be a reactant. And in other words, it's gonna be the oxidant, okay? Or the higher oxidation, the oxidizing agent, and therefore the reaction, the E is likely to be higher than the iron E naught, sorry, E naughts for both. Or the E even for Ag is higher than the E for the Fe. Well, assuming that, we have on the reduction half reaction, the Ag plus 1 electron, and the oxidation will be my iron reaction. Iron 2 plus goes to iron 3 plus. The number of electrons exchanged in each is 1 electron. Get a global reaction, and there's our global reaction. Now, initially we have 0.1, 0.1. Notice they did not give me volumes, so I don't have to correct this. This is, again, an assumption that if they don't give you volumes, that these concentrations are the concentrations already in my solution after the mixing. They tell us that the final at equilibrium is 0.08. That means that the amount reacted has to be minus 0.02 or 0.02. Once I have the amount reacted, I could solve for all the others. This is the iron 2 plus will also be minus 0.02, and the iron 3 plus on this side is plus 0.02. I don't really include the solids because they don't get into my equilibrium constant. Great. Now I have the concentrations at equilibrium. It's from here that I can get K. And the biggest question is, why didn't I do that? Why didn't I get K initially? Is because I don't have, again, the E naught for the Ag couple, and I still don't have it. Okay, so get the K, products divided by the reactants, okay, to the stoichiometry, which is 1, 1, 1. Put in the numbers, number crunch it at equilibrium, and we get the K is 3.14. Clearly this K is not quantitative and it's not complete. Therefore, I can't notice. Of course, I didn't put 0. None of these became 0 and at equilibrium because the K is not large. Now from the K, we're going to find the E naught. How do we do that? This is again new. First, get the delta E from the K. So we have the K, get delta E naught. Delta E naught will be log K times the 0.592 divided by the number of electron transferred, which happens to be 1, and get the delta E naught. Once you have the delta E naught, that's E naught of the reduction minus the E naught of the oxidation, or reductant minus the oxidant, and I prefer the reduction minus the oxidation. Delta E naught, because the reduction half has the strongest oxidant or oxidizing agent, equals E naught of the Ag minus the E naught of the iron. Solve for the E naught of the Ag, since we have the delta E, will be delta E naught plus E of the Fe couple. Again, you can call this E naught of the cell or without the delta as you wish. Solve, you get 0.8 for the E naught of the Ag. This was an indirect reaction. You're given the one of the material concentration at equilibrium. You end up finding the concentration of all the other species at equilibrium. You solve for the K from the concentration, then you get the delta E from the K. At equilibrium, we know that the overall reaction free energy is 0. The overall delta E of the reaction is 0. And so the reduction potentials of each of the couples should be equal, and that will be the potential of my solution at equilibrium. Just as a test, go ahead, get it for both couples. I would personally not get it for the iron if I had the choice. I just simply get it for the Ag because I have the concentration of Ag plus already at equilibrium, and therefore, you know, I don't have to do further calculation. Well, but now we had no choice. We were asked for different calculations. So we also have that iron concentration at equilibrium. This is proving to you that you could use either the iron couple or the Ag couple to get the E at equilibrium. Again, for titrations, this is important because I don't have to get it for both couples. As long as I have it for a single couple, I have the Ag at the E at equilibrium for a mixed solution in one pot. Actually, it's the same even if it was separate pots. If they were two half cells separated, that's exactly the same. It doesn't change. The E at equilibrium, the E in one vessel will be the same as the E in the other vessel once we reached equilibrium. So when you do these reactions, it doesn't differ if you have a single pot or a redox mixture in the same pot, in two different pots.